I want to thank organizing committee for inviting me. Okay. If the previous talk is on the microscopic mechanism of speech generation, my talk will be on the global mechanism of dynamic evolution of human knowledge system. Okay. And this was done as a colleague. So human knowledge system is a kind of a complex system with many concepts and relations between them. And recently, again, network analysis is quite useful for the calculation of the complex system. For example, like a gender relation network from protein interaction or World Wide Web or social network. So then, I will provide the network analysis for the realization of the global organization of knowledge systems, specifically in physics textbook. So for that, I will I've described the static properties by the degree distribution of Cartesian quotient, and the dynamic properties will be described by the interdependent distribution or time correlation function and the dynamic continuous function. And finally, I will present mathematical models describing the properties of the large network system. Then I will briefly comment on the past application. So we use three physics textbooks, three in Korean and three in English. And additionally, we also analyzed one physics dictionary. And in case of one of the textbook, which is physics, the number of sentences is about 10,000, and the number of physical terms are about 680. And total occurrence of physical terms are about 22,000. So on the average, in one sense, we have two concepts. So to construct the net, we need a node and a link. So node corresponds to physics terminology appearing in the textbook. Of course, we are limiting to the terminology listed in the physics dictionary. And in case of a link, it is quite controversial. But anyway, for simplicity, if two nodes occur one sentence, then we are assuming that there is a link between two nodes. So in case of this sentence, there are 8 terms, and then they are occurred in one sentence. Then we are assuming that there is an all-to-all connection between them. Okay? And then we characterize this kind of network. And in case of this textbook, the frequency is not all the same. So here we are listing top list. Both is the frequency of both is about 1,000, and the next to be the data and something this one. This might be the most important physics terms appearing in the textbook. So we characterize by the textbook. First, by the frequency distribution. This is the frequency and this distribution. And for six textbooks, they all follows how behavior is R around 1.5 and 2.0. So this is a very long useful. And also the co-occurrence. For example, two physical terms. The frequency of the co-occurrence is not the same. Okay? This is also how behavior this one. And this will be a match of the information between two links. And this will be quite useful for constructing weighted network. But right now, here I'm just focusing on the binary net without weighting. So to characterize the network structure, typically we count the degree for each node. For example, and actually this will be the network. with again the degree distribution. Typically, the degree distribution, the degree, okay, the fraction decreases with k, like this one. This kind of degree distribution is well, okay, observed in many complex systems. For example, like the tracking network, World Wide Web, protein interaction. This could be called, okay, this kind of behavior we call scarcity distribution. One important feature of the complex network, and the importance is the presence of organelles like this one. And another method we calculate is the local crossing coefficient. The local crossing coefficient is defined, for example, the local crossing coefficient is defined as the fraction of connection between neighbors. For example, here, this one has so many neighbors, and how many of them are connected to each other. Okay? This is the local crossing coefficient. So in case here we have a node and we have many connections. If there is no connection between them, then in that case the local crossing coefficient is 0. But in case, for example, around here, this one has connection to this one, and they are connected all to one. In that case, the crossing coefficient is 1. And typically, okay, for complex system, we have the dependence of a local crossing coefficient as a function of k, if the case like this one. This kind of dependence is known as a hybrid organization. It is very like the organization of a big company. For example, the boss is like the hub and the hub, and there are so many folks working in this company knows this hub, but between these people, they don't know each other. It's just a fraction. But okay, some member of a small team, they have a small connection, but they know all to all. So typically, that kind of system, we have a dependence like this one. And this is, okay. Actually, the whole network structure is so complicated because they are densely connected. So here, I'm presenting the most important part with degree, okay, equal to 10. Then here, we are plotting, okay, the color convention is the color represents a different category of physics. For example, the red one represents mechanics part, and this part represents wave optics, and this part represents electromagnetism. So this kind of construction is very nice, still not less. We can see this kind of construction is quite meaningful. Okay. And this is a summary of characteristics of a technical network. Okay. The system size varies from around 200 to 2,000. But here, this represents mean distance between any two nodes. Okay. The distance is very short, and it does not change much. Why? If this system size increase, the degree is quite big number, and it also increases number of size. This is the reason why the mean distance is not growing, it remains constant. And the degree exponent, the gamma is less than 2. Typically, we observe this kind of behavior when the network system size is increasing very fastly. Okay, this is a summary of a static property. Then I'm moving to the dynamic aspect of the dynamic loss. Okay. Typically, in one textbook, one physical term, they are appearing so many times, but they are not occurring uniformly in the equal interval. They are very non-uniform. For example, here I'm plotting the cumulative frequency. And in this case, this one occurs at one time, almost in short interval, then we need very constant. This is almost the same, and this is almost the same. But in this case, the green one. Throughout the whole textbook, the frequency increases gradually. Okay? This is a homogeneous one, and this is a non-homogeneous one. We can quantify this kind of non-uniformity by the difference between the diagonal represents uniform curve, and the diagonal line and the frequency curve. This is defined as non-uniformity. Okay? So here we are plotting for each node, the scatter plot of frequency and the non-uniformity, and the red represents the physical terms of in the textbook, and they are scattered all over this pen. And the magenta represents randomly shuffled textbook. For the original textbook, we randomly shuffling the ordering of the sentence. Then the frequency, the occurrence is that become rather uniform. So they are line along here. This line represents the most for each frequency, the most frequency, the value of non-uniformity when the nodes are fitting uniformly. This is the minimum line. So for the random textbook, the non-uniformity is very close to the minimum line. And this kind of non-uniformity could be also characterized by the inter-event interval distribution. Interval between events. Here, event is the occurrence of physical terms in the textbook. Typically, this kind of random process we expect Poisson distribution. The interval is exponential in time. Okay? But actually, for this kind of textbook, the interval shows at the first decade. For certain period, the firing rate is very high, but we have a long period without firing. So in this case, interval distribution is how decay. Okay? This is the result. And the slope is about 1.5 for all textbook. Here we are presenting the result of random textbook and also the dictionary. This is kind of different from this textbook. And another feature of the textbook growth is it has a time correlation. So here we are measuring sentence to sentence time correlation. It is defined by the number of overlapping physical terms between two sentences separated by time interval t. Okay? And it shows for three textbooks, the correlation function decay in power. Okay? So it has long range time correlation. This is an important feature of the textbook. But in case of the dictionary, the behavior is quite different. Typically, one item in physics dictionary, it is described by about 10 sentences. So within 10 sentences, the correlation is preserved. But beyond that, okay, the correlation is completely lost. Also, in case of a random textbook, the correlation is lost. Okay. So, how can you understand this kind of behavior? So, recently, Baramasi tried to understand this kind of human behavior dynamics. For example, in recent two papers, he analyzed the correspondence patterns of the Darwin and Einstein. And this is the time of first of all Darwin, and then he received a lot of letters, and then he responded. Okay, the red one represents the time of his response, and this is the data of Einstein. And then he analyzed time interval between the receiving data and the answering data. And the time for the for the time interval, the distribution shows this kind of power behavior. Okay, this kind of power behavior. So this is the first behavior. He tried to explain how this kind of behavior can be generated. Actually, this kind of behavior could be obtained in large of human behavior. For example, the frequency of we frequently make a print out. What is the interval of between two printing? And sometimes we are borrowing goods from the library. What is the interval distribution? All of these data, human behavior data, shows behavior something like this. How this can be obtained? Okay? He explained this kind of human behavior dynamics in terms of the two system. Okay? For example, for each letter he received, it has some kind of priority. Some letters important, some letters less important. Then, depending on the priority, he is responding. Okay? At first, he responds to the most priority one. Then, by that kind of queuing system, he could explain this kind of behavior. So, now I'm going to describe the textbook flows as kind of queuing system. But here, it is a little different. For example, for each sentence, we have several new concepts and old concepts. Old concept means this is a sequence of a sentence, and now I am preparing a new sentence to be added here. Okay? To make a new sentence, okay? Some of them, okay, here this is the new and this is the old one. To get this one, new one, we get from pool of knowledge system. Okay, this is the pool of concept, and also from this one. And here we are assuming that new concept is introduced randomly from this pool. And for this one, it is selected with certain priority, depending on the priority. Okay? Here we have two effects, okay? Like evolution in nature. We have two effects competing. One is natural selection, the other one is inheritance. These two makes our nature evolve. Very like that, we have two effects. First, when you write a new sentence, we have a tendency of introducing important concepts. Okay? This we call net effect. Also, we have a tendency of repeating some concept used just previously. Okay? We call this memory effect. Okay? By these two effects, we are going to explain all the static properties of knowledge network and dynamic properties of textbook blocks. So, for the network model, okay, the selection probability for the sentences, the selection probability depends on the degree. Okay? Here we can use either degree or frequency, but actually degree is proportional to the frequency. Okay? So they are not much different. So we are using degree. So in case that is very small, it corresponds to random selection. So bias for the whole. In that case, it is a random processor, so it shows event interval distribution shows awesome exponential behavior. But when that is quite big enough, then we have power behavior in the event interval distribution. Also, here we are showing the degree distribution versus number of nodes. And when that is small, it is very like exponential, but when that is quite big enough, it shows power behavior. in this case, the problem is it does not show any time correlation. This is a textbook, and this is the result of the network model. It does not provide any time correlation. So in case of a network model, the selection probability time display here how represent time interval between present sentence and previous one. So like this one, the selection probability of the most recent one is higher. And so alpha less than, but the smaller one, it is a random. So it is a very like previous case with beta very small. And this one and this one. When alpha is very high, in this case, we have a strong bias for the most recent one. In that case, okay, for short time interval, we have a very high time correlation. Okay? But for long time, the correlation decreases very, very rapidly. So it shows exponential. Why? We have sequence of a sentence, okay, and the new sentence is connected to the old sentence by sharing some dot. But sometimes we have a new sentence without old concept. Sentence with just new concept. Okay? Then the sequence of the sentence is interrupted. Okay? Because of this one, the time correlation decreases exponential. Also, because of that, and when after that big, the system size does not grow much. Okay? So instead, when R equals 1, then post 1, we have a good time correlation behavior and the power behavior in the event interval distribution. But the problem, the system size is much smaller than the textbook. So, as a summary, the network provides scale-free distribution, very large connectivity, and the memory model provides long-time correlation. So combining these two, actually when it like, we utilize both strategies. So the real textbook could be explained by the combination of these two. So with weight WM, we are selecting this one, and with WM, another weight, we are selecting this one. Then we could explain most of the properties of textbook. So now we have constructed mathematical model describing the textbook. So now we want to know what is the effect of a large network structure on the learning efficiency. Okay? What is the relation between learning efficiency and the structure? Okay? For that, we are using the Ebbinghaus forgetting curve. The capacity of the learning, it depends with exponentially. So we adopt this model for the weight of link. So the link weight increase with introduction of a pair. It increases, then it decays exponentially. Okay? So this will be accumulated with time. When the accumulated weight crosses a threshold value, then we are assuming that this is on the learned scale. Okay, so here I'm showing some moving, mimicking the process of learning. But instead of presenting texture, I will present the sum. Okay, like in case of textbook learning, the knowledge system is growing gradually, and starting from homework, gradually expand. But in case of dictionary learning, sometimes it learns very, very intermittently. Short period it learns a group, and then as a learning another group, then the previous one is a programmer. So in this case, textbook learning, it goes gradually. This sound, you can understand what I'm meaning, but unfortunately, we don't have sound. So dictionary learning is very like this one. At one time, we have one item is learned, but as a learning, another item, the previous one is forgotten, something like that. And then we analyzed the community structure like this one, how the community structure is evolving in time. Okay, this is the result of analysis of time community structure. Here I am plotting the size of a community and vertical represent the lifespan of the community. So in case of a textbook, we have quite a big community lasting for a long time. Okay? Of course, there are lots of small community that's short. But in case of a dictionary, we have a very big community, but they are lasting very shortly. Okay? And to test what kind of properties contribute this kind of good memory and good learning. Okay? We tested this model first. Okay? So in case of a memory model, alpha 0 as very large maximum degree, but it has a very weak time correlation. So in that case, the process size is quite big, but the duration time is very short. Okay? In case of a very large alpha, it has a very short time correlation and a small maximum degree. So both T and S is small. Okay, like this one. When alpha is around 1, it has a long time correlation and also very large maximum degree. So in this case, we have a very large T and very large. So here we are plotting the size of the biggest cluster, and here also the duration time. As mentioned, the cluster size decreases with alpha, but the duration time increases at first, then decreases later because of the method I mentioned. So the maximum capacity of learning could be obtained at this point. This point is real. It has both long time correlation and very large maximum degree. So fortunately, for the textbook I introduced, they all have long time correlation and very large maximum degree. This is the reason why it could maximize learning efficiency. So we can utilize this kind of property to optimize our